So we've seen two different types of equilibrium constants, one for the gas phase, which we call Kp, and one for the aqueous phase, which we call Kc. And these can be different values or they can be the same. It depends upon the balanced chemical equation. Sometimes Kp and Kc are equal, sometimes they're different. So how do we know what the relationship between the two are? Well, the equilibrium constant in the gas phase is equal to the equilibrium constant in solution if you multiply it by the gas constant R times the temperature T in Kelvin and raise that to the power of delta N, where delta N is the number of moles of gas as a product from the balanced equation minus the number of moles of gas as a reactant. To give you an example of this, we'll go back to Haber's reaction and look at it in solution. And here we've got the equilibrium constant in solution. So this is the Kc value. And if I want to know what the equilibrium constant for the reaction is in the gas phase, well, I apply Kp equals Kc times RT raised to the power of delta N. And then what I can do is I can say Kc is 9.6, R is 0.0821 or 806, depending upon which version of R you like to use, times the temperature 300 degrees Celsius, except we have to change that into Kelvin. So 300 plus 273 gives us 573, so that's where the 573 comes from, is that temperature in Kelvin, and then raised to the power of minus 2. Why is it minus 2? Well, N is the number of moles of product that would be a gas, 2, minus that of the reactants, which there's 1 N2 and 3 H2, so that's how we get minus 2 here. So we can then go through and plug and chug our values, and lo and behold, we get Kp equals 4.34 times 10 to the minus third for this reaction. Now this is an important thing to note because the meaning of the equilibrium constant is important. When we talk about equilibrium constants, we're talking about ratios of products to reactants. So one thing to remember is equilibrium constants are always positive values. They can never be a negative value, nor can they be 0. Second thing, if the equilibrium constant is greater than 1, that means the ratio of products to reactants favors product production. If the equilibrium constant is less than 1, that means products are not favored. This is a reactant-favored reaction. So being able to interpret the meaning of the equilibrium constant is going to be important into informing us what we know about the reaction. In the previous slide here, we saw that Haber's reaction in solution has a K value of 9.6, which means that it would be a product-favored reaction in solution. However, going into the gas phase, this reaction now has an equilibrium constant less than 1, meaning that it's reactant-favored, which really created a problem for Haber, and one of the reasons he had so little ammonia being created at any given instant. So the meaning of equilibrium constants is important for us to understand where the value of K lies with respect to being a product-favored or reactant-favored reaction.